Welcome back. This is the fourth in a series of video posts where we explore diagnostic process mining. In the last video post, we discussed how we identify the causes of a problem using a causal diagram and estimating the causal effect. In this episode, we'll be exploring how we can prove or validate the accuracy of these causal estimates. In other words, how we can check whether or not the assumptions that are implicit in our causal diagram are supported by observed data. A reminder that this is the fourth in a six-step diagnostic process mining workflow. We start by briefly revisiting the meaning of causality. The variable x can be said to cause y if a change in x causes a change in the probability of y occurring. So say x is the average case complexity score and y is the average case cycle time. If a higher case complexity score causes longer case cycle times, we expect to see cycle time increase as case complexity increases and vice versa. However, if there's no relationship between case complexity and team height, as we vary the case complexity, the team height stays unchanged. So if you watch the last video post, we specified a causal diagram which formed the basis of the estimation of the effect of a causal factor that we're interested in, that is, does chasing or repeatedly contacting customers increase or decrease the probability that they will accept a loan offer. However, the accuracy of that estimate depends on the structure of the specified causal diagram. So, for example, we specify here that the credit score impacts the payback period, which in turn impacts the probability of acceptance. But if that causal structure does not reflect reality, then a causal estimate will be incorrect. Or here we specify that the credit score affects both the monthly cost of borrowing and the first withdrawal amount. But again, if the assumption is wrong, then our causal estimates will be incorrect. The question though is, how do we validate that our model assumptions are robust? Well, in this post, we're going to specify a number of ways in which you can do that. But first, let's take a closer look at the various measurements of treatment effect. Treatment effect answers the question, what is the effect on the outcome when we apply a particular intervention? And if you recall from the previous post, the solution or intervention of interest is also referred to as the treatment. There are various measurements for the treatment effect, but let's start by examining the individual treatment effect. This is calculated by the formula you can see on screen. This in effect is the difference in the outcome when an individual is treated compared to when the same individual is not treated. To help understand this, imagine you have a headache and you took a painkilling tablet, and within 15 minutes, the headache was gone. Later on, though, you have another headache, but you don't take any medication, perhaps because you've run out of tablets, and this time your headache persists. If the desired outcome is to get rid of your headache, then we can assume that that painkiller has had a positive treatment effect. In our example, our treatment effect is the difference between when an individual is chased, say they accept, and when they are not chased, say they decline the loan offer. In that case, we say that chasing the client has a positive treatment effect. However, there could also be a neutral treatment effect where chasing the customer doesn't make a difference, or a negative treatment effect where chasing the customer has an outcome, has an effect opposite to the one we intended. The individual treatment effect is also known as the unit level treatment effect. And this treatment effect will differ from individual to individual because well, we are all different. As such, it's the best assessment for a causal estimate as it allows for more targeted intervention. However, the problem with causal inference is that unlike for a predictive model, where you can compare your prediction against the ground truth, with causal inference, we can only observe one outcome or the other. If we have chased customers, we can go back in time and unchase them to see what the outcome will have been. This is what's described as the fundamental problem of causal inference. Before we move on, though, one point to make is, although we refer to an individual in this example, the unit that is treated could be anything. It could be a widget, it could be an order, whatever goes through your process. To get around the fundamental problem of causal inference, we use the average treatment effect. And the average treatment effect is the total difference in outcome between when no one is treated, that's also referred as without the policy, or when everyone is treated under the policy. In this example, when everyone is treated, 4 out of 5 individuals accept their offer, but when no one is treated, only 1 out of 5. Again, that indicates a positive treatment effect. However, this is a relatively blunt instrument as it doesn't cater for individual differences. It's been jokingly said that on average, if I stick my feet in the oven and my head in the freezer, I'll be fine. There's also another treatment effect of interest referred to as the conditional average treatment effect. This is where we calculate the average treatment effect based on a certain condition, for example, on the credit score. So here we see, here we calculate the difference in treatment effect when we compare customers with a credit score below the median with those with a credit score above the median. And we may find that those with a lower credit score have a positive treatment effect, but those with a higher credit score have a negative treatment effect. This enables us to effectively target the right group of customers with this intervention. We'll discuss more on this in the next video when we discuss uplift modeling. So how can we validate our causal estimates? One of the main ways we do this is by SME or subject matter expert validation. In the previous post, we recommended that the causal diagram be created in conjunction with subject matter experts. And I believe this is one of the main advantages in using a causal diagram to specify your causal relationships and make your assumptions transparent. For example, I made the assumption that customers with a high credit score are more likely to be chased than customers with a lower credit score. Now, that seems like a reasonable assumption because any lender would generally prefer a higher quality loan book. However, is that the way this Dutch financial service firm operates in practice? I don't know. However, an SME will be able to confirm, yes, this is what we do, in which case we retain that causal link, or no, we don't do that, in which case we delete the link. The point, though, is the assumption is transparent for anyone interested to observe and validate. Having completed SME validation, we can now validate assumptions by checking whether those assumptions are supported by the data. And we'll discuss 2 ways in which we can do this. The first is by testing the implications implicit in our causal diagram. You may recall from the last video that if you missed that video post, I would recommend you watch it. One of the advantages of using this tool is that it makes those implicit assumptions in our causal diagram explicit, and we can then test whether these assumptions are supported by the data. You recall when we discussed the atomic structure of causal diagrams in that last video post, we mentioned that a confounder will make 2 or more variables appear correlated. We also mentioned that the causal factors that form a collider should not be correlated. So from our specified causal relationships, we can expect the presence or absence of some associational relationships. So let's interpret the testable implications that Daggett has generated for our causal diagram. At first glance, it may appear confusing, but let's pick on that one. Reading from left to right, we first come across what looks like an upside down T. This symbol stands for is not correlated. So that reads first withdrawal amount is not correlated with payback period. As we read on, we come across what looks like a line. And that symbol stands for given the same level of. So that testable implication can be read in full. The first withdrawal amount is not correlated with payback period, given the same credit score. In other words, if we examine customers with the same credit score, we should not observe any correlation between the first withdrawal amount and the payback period. And we can check if this is the case from the data in the event log. On screen, you see the results from testing these assumptions. There's a link to the code used to generate this result in the comment section. The two tests we need to perform for each of these implications. First, we check that the estimate, that's the second column in the table, should be around 0. And second, we check that the p-value, that's the third column in that table, should be no higher than 0.05. If both tests pass, then we can safely retain that causal assumption. However, looking at results, we notice 3 implications that are not supported by our data, which may suggest that we need to revisit our causal assumptions. One final thing to note if you're going to use Daggett to generate this, one, the variable names in the causal diagram have to be identical to those in your data frame. And second, if there are any unobserved variables, then they should be removed from the causal diagram. The second way that we use our data to test implications is by checking how sensitive those assumptions are to change. This is also referred to as refutation. I'll briefly discuss a number of ways we can attempt to refute our assumptions using sensitivity analysis. The first 2 techniques involve adding an unobserved common cause. Now, if those causal assumptions are correct, then the causal estimates should not change much for both refutees. The first technique involves adding a random common cause to any 2 variables in our causal diagram, as we've done here. Now, adding a synthetic independent random variable as the common cause should not affect the estimated causal effect, and we can see from a result that the new estimate, is relatively unchanged. The second technique involves adding an observed common cause to the treatment and the effect, as we see there. Again, if the assumptions are robust, they should not be sensitive to the additions of this common cause. And as we can see there, our new estimate is relatively unchanged. Another sensitivity analysis technique involves creating a subset of the data. When we replace a given data set with a randomly selected subset, the estimated effect should not change significantly. And we see from the result there that that's the case. There are other refutation techniques which involve replacing the treatment or intervention with a placebo. When we do that, we expect the estimated causal effect to go to 0, or replacing the outcome variable with an independent random variable. Again, when that happens, we expect the estimated effect to go to 0. As mentioned earlier, there's a link in the comment section for the code base, as well as a number of other resources which go into more details on these techniques. In summary, though, it appears that our causal diagram needs revisiting as some of the assumptions are not supported by the data. In a real-world project, I will recommend you reconvene with your subject matter experts, look at each relationship, amend the causal diagram, and then retest whether or not the data supports your assumptions. As I don't have access to subject matter experts for this process, I'm unable to do that. In the previous video, we estimated that the causal impact of chasing customers on acceptance rates, but we found that that effect was fairly negligible. Now, let's assume we've amended our causal diagrams, we calculated the causal effect, and it was still very low. That's a useful result in as much as it saves us from wasting resources, implementing a solution that doesn't improve acceptance rates. The question, though, is how can we find solutions that improve acceptance rate? Solutions that move the needle, as it were. In the next video, we'll be looking at how we can identify potential solutions that have a significant impact. Hope you join us for that video.